Download this code from codegive.com, link in the description below. Understanding race conditions in concurrent programming, a comprehensive tutorial. Race conditions are a tricky and often subtle problem in concurrent programming. They occur when multiple threads or processes access and manipulate shared data concurrently, and the final outcome of the execution depends on the unpredictable order in which these threads/processes execute their instructions. This non-deterministic behavior can lead to unexpected and incorrect results, making them difficult to debug and reproduce. This tutorial will delve deep into race conditions, covering 1. What is a race condition? Definition, key characteristics. 2. Why are race conditions a problem? Impact on program correctness. 3. Necessary conditions for race conditions, what circumstances lead to them? 4. Types of race conditions asterisk. Asterisk data race asterisk the most common type. Asterisk check then act asterisk a classic example. 5 code examples, Python, Java, C++, illustrating the issue and potential solutions. 6 how to identify race conditions, tools and techniques. 7 how to prevent race conditions, synchronization mechanisms. Asterisk locks, mutexes. Asterisk semaphores. Asterisk atomic operations. Asterisk condition variables. Asterisk thread-safe data structures. 8 avoiding race conditions through design, strategies for minimizing shared state. 9 common mistakes and pitfalls. 10 conclusion. 1. What is a race condition? A race condition arises when the outcome of a program execution becomes dependent on the relative timing of multiple concurrently executing threads or processes. Essentially, different execution orders can lead to different results. This happens when asterisk shared data asterisk multiple threads access and modify the same data. Asterisk unprotected access asterisk access to this shared data isn't protected by any synchronization mechanism. Asterisk non-atomic operations asterisk the operations being performed on the shared data aren't atomic, indivisible. A seemingly single operation might actually be broken down into multiple CPU instructions, allowing another thread to interleave its execution in between. Key characteristics asterisk. Asterisk non-deterministic asterisk the result varies from one execution to another, even with the same inputs. This makes them notoriously hard to reproduce during debugging. Asterisk intermittent asterisk they may only manifest under specific conditions, such as high CPU load or a particular sequence of events. Asterisk difficult to detect asterisk they often don't cause immediate crashes or errors. Instead, they can result in subtle data corruption or incorrect program behavior. 2. Why are race conditions a problem? The primary problem with race conditions is that they compromise the correctness and reliability of your program. They can lead to asterisk data corruption asterisk shared data can be left in an inconsistent state, leading to unpredictable behavior. Asterisk incorrect results asterisk calculations or operations might produce wrong results because of the interleaved execution. Asterisk deadlocks asterisk race conditions can sometimes contribute to deadlocks, where threads become blocked indefinitely, waiting for each other. Asterisk security vulnerabilities asterisk in some cases, race conditions can be exploited by malicious actors to gain unauthorized access or manipulate data. Asterisk difficult debugging asterisk the non-deterministic and intermittent nature of race conditions makes them incredibly challenging to debug. Traditional debugging techniques like breakpoints and stepping through code may not reveal the underlying problem. 3 necessary conditions for race conditions. For a race condition to occur, the following conditions must generally be met. Asterisk concurrency asterisk multiple threads or processes must be executing concurrently, either truly parallel on multiple cores or interleaved using time slicing. Asterisk shared mutable state asterisk the thread/processes must be accessing and modifying the same shared data. If the data is read-only or if each thread has its own private copy, race conditions are unlikely. Asterisk lack of synchronization asterisk there must be a lack of appropriate synchronization mechanisms, like locks, semaphores, or atomic operations, to protect access to the shared data. If any of these conditions are not met, race conditions cannot occur. 4 types of race conditions. While all race conditions stem from the same fundamental issue, unprotected concurrent access to shared state, they can be categorized into different types. Asterisk data race asterisk this is the most common type. It occurs when 2 or more threads concurrently access the same memory location, and at least one of them is writing. The order in which the threads read and write to the memory location determines the final value. This violates data integrity. Asterisk check then act asterisk this type of race condition involves a sequence of 2 operations. 1 check asterisk a thread checks the value of a shared variable. 2 act asterisk based on the value it read in the check step, the thread performs an action that modifies the shared variable. The problem is that between the check and the act, another thread might modify the shared variable, rendering the check's result obsolete. This can lead to unexpected or incorrect behavior. A classic example is the double-checked locking pattern, which is often flawed due to check-then-act race conditions. 5 code examples. Let's illustrate race conditions with code examples in Python, Java, and C++. Python example, data race. Explanation asterisk. Ideally, the final counter value should be 2 asterisk number underscore increments, 200,000. However, because counter plus equals 1 is not an atomic operation, it involves reading, incrementing, and writing, threads can interleave their execution. This leads to a data race, and the final counter value is often less than expected. Run this multiple times and you'll see varying, and often incorrect, results. Java example, check then act. Explanation asterisk. This example demonstrates a check then act race condition. Multiple threads might simultaneously check if the balance is sufficient to withdraw a certain amount. If they both see that the balance is enough, they both proceed to withdraw, potentially resulting in the balance becoming negative, even though each individual check indicated sufficient funds. The thread.sleep call exaggerates the effect. C++ example, data race. Explanation asterisk similar to the Python example, the counter plus plus operation is not atomic. Threads can interleave, leading to a data race and an incorrect final counter value. 6. How to identify race conditions. Detecting race conditions can be difficult, but here are some techniques. Asterisk code review asterisk carefully examine your code for sections where shared data is accessed by multiple threads/processes without proper synchronization. Asterisk static analysis tools asterisk these tools can analyze your code and identify potential race conditions based on patterns and data flow. Examples include Clang's thread safety analysis for C++, find bugs for Java, and various linters for other languages. Asterisk dynamic analysis tools asterisk these tools monitor the execution of your program and detect race conditions at runtime. Examples include asterisk thread sanitizer, tsana a dynamic data race detector for C/C++, part of LLVM. Asterisk hellgrind asterisk a thread error detector for C/C++ code, part of Valgrind. Asterisk Java concurrency testing libraries asterisk libraries like JakeStress in Java are specifically designed to create and run micro benchmarks that expose concurrency issues. Fuzzing. Fuzz testing involves feeding your program with a large amount of randomly generated input data. While not specifically designed to find race conditions, it can sometimes uncover them by triggering unusual execution paths. Stress testing. Run your program under heavy load and monitor its behavior. Race conditions are more likely to manifest under high concurrency. Tools like Stress, Linux, can simulate CPU load, memory pressure, and I/O activity. Code instrumentation. Add logging statements to your code to track the order in which threads access shared data. Analyze the logs to identify potential interleavings that could lead to race conditions. Be aware that adding logging can sometimes change the timing of events and mask the problem, debug. Reproducibility techniques. Although difficult, try to make your test environment as reproducible as possible. Use the same hardware, operating system, compiler versions, and even set the same environment variables. 7. How to prevent race conditions. The most effective way to deal with race conditions is to prevent them from occurring in the first place. Here are several synchronization mechanisms to protect shared data. Locks, mutexes. Mechanism. A lock, or mutex, mutual exclusion, allows only one thread at a time to access a shared resource. A thread must acquire the lock before accessing the resource and release it afterward. How it prevents race conditions. By ensuring exclusive access, locks prevent multiple threads from interfering with each other while manipulating shared data. Example, Python. Important. Always release the lock, even if an exception occurs. The with statement, in Python, or finally block, in Java, can help ensure this. Failing to release a lock can lead to deadlocks. Semaphores. Mechanism. A semaphore is a generalization of a mutex. It maintains a count of available resources. A thread must acquire a semaphore before accessing a resource, decrementing the count, and release it afterward, incrementing the count. The semaphore allows a specified number of threads to access the shared resource concurrently. How it prevents race conditions. Semaphores are useful when you need to control the number of threads that can access a resource concurrently, rather than allowing only one thread at a time. Use cases. Limiting the number of connections to a database, controlling access to a pool of resources. Atomic operations. Mechanism. Atomic operations are indivisible operations that complete in a single step, without being interrupted by other threads. Most programming languages provide atomic operations for basic data types, integers, booleans. How it prevents race conditions. Atomic operations guarantee that reads and writes to shared variables are consistent, even when multiple threads are accessing them concurrently. Example, C++. In C++, the atomic header provides atomic data types and operations. Condition variables. Mechanism. Condition variables are synchronization primitives that allow threads to wait for a specific condition to become true. They are always used in conjunction with a mutex. How it prevents race conditions. Condition variables allow threads to efficiently wait for a shared resource to become available without busy waiting, repeatedly checking the condition. They help avoid spurious wake-ups by requiring threads to recheck the condition after being woken up. Thread-safe data structures. Mechanism. Some data structures are designed to be thread-safe, meaning that their internal operations are synchronized to prevent race conditions. Examples. Concurrent hash map, Java, concurrent queue, C++. These data structures handle the synchronization internally, so you don't need to worry about explicitly locking and unlocking. However, operations involving multiple methods on the thread-safe data structure may still need synchronization. 8. Avoiding race conditions through design. While synchronization mechanisms are essential, the best approach is to design your code to minimize the need for shared mutable state. Here are some strategies. Immutability. Use immutable data structures whenever possible. Immutable data cannot be modified after it is created, so there's no risk of race conditions. If a thread needs to modify the data, it creates a new copy with the desired changes. Thread confinement. Restrict access to shared data to a single thread. This thread becomes the owner of the data and is responsible for all modifications. Other threads can communicate with the owner thread to request changes, but they never directly access the shared data. Message passing and actors are common patterns to implement this. Functional programming. Embrace functional programming principles, which emphasize pure functions, functions that have no side effects and always return the same output for the same input, and immutable data. This greatly reduces the potential for race conditions. Avoid global variables. Global variables are often a source of shared mutable state. Minimize their use and try to encapsulate state within objects or modules. Use higher level abstractions. Instead of directly manipulating threads and locks, consider using higher level abstractions such as thread pools, futures, and reactive streams. These abstractions often handle synchronization internally, making your code less error-prone. 9 Common mistakes and pitfalls. Forgetting to release locks. This can lead to deadlocks. Use try, finally blocks, Java, or with statements, Python, to ensure that locks are always released, even if exceptions occur. C++ SRAII, resource acquisition is initialization, is very useful in this regard. Incorrect lock granularity. Coarse-grained locking. Using a single lock to protect a large section of code can reduce concurrency and performance. Fine-grained locking. Using too many locks can increase overhead and complexity, and can also lead to deadlocks if locks are acquired in different orders by different threads. Deadlock. A situation where two or more threads are blocked indefinitely, waiting for each other to release a resource. Deadlocks can be caused by circular dependencies between locks. Avoid holding multiple locks simultaneously if possible. If you must hold multiple locks, always acquire them in the same order. Live lock. Similar to deadlock, but instead of blocking, the threads repeatedly attempt to acquire resources but fail to do so. Spurious wake-ups. Condition variables can sometimes wake up threads even when the condition they are waiting for is not true. Always recheck the condition after being woken up by a condition variable. Priority inversion. A high priority thread can be blocked by a low priority thread that is holding a lock. This can be mitigated by using priority inheritance, where the low priority thread temporarily inherits the priority of the high priority thread. Bugs. Race conditions can be masked or altered by the act of observing them, example by adding logging statements. This makes them incredibly difficult to debug. 10 Conclusion. Race conditions are a significant challenge in concurrent programming. They can lead to subtle and hard-to-detect errors, compromising the correctness and reliability of your software. By understanding the causes of race conditions, using appropriate synchronization mechanisms, and adopting design principles that minimize shared mutable state, you can effectively prevent and mitigate these issues. Remember to test your concurrent code thoroughly, using static analysis tools, dynamic analysis tools, and stress testing to identify potential race conditions early in the development process. Concurrency is inherently complex, and there's no silver bullet for avoiding race conditions. Careful design, attention to detail, and a solid understanding of the underlying principles are essential for building robust and reliable concurrent applications.